Ladies and gentlemen, members of the Board of the Zeeuw Generale, Dean of the Faculty of Science and Engineering, honored guests, my name is Scott Traeger. I am the Director of the Kaptein Astronomical Institute here at the University of Groningen, and I want to welcome you all tonight to this lecture. I want to particularly extend a welcome to Professor Blaauw's 3 daughters, who are all joining us tonight. It is very special for us to see you here tonight, and that leads me to welcoming you all to the 2018 edition of the annual Blaauw Lecture, which will be given tonight by Professor Tim de Zeeuw of Leiden University. I will now actually hand the introduction over to Professor Amina Helmi, also of the Kaptein Institute, host of this year's lecture.
Ladies and gentlemen, good evening. I would like to start by giving you a bit of background on the Blaauw Lecture. The Blaauw Lecture is given once per year by a distinguished scientist in the field of astronomy. It honors the memory of Professor Adrian Blaauw, who made outstanding scientific and organizational achievements and had an extremely important impact on astronomy here in Groningen, in the Netherlands, and in the whole world. Professor Blaauw was director of the Kaptein Institute at the University of Groningen from 1957 to 1968 and was one of the founding fathers of the European Southern Observatory, being its first Director General. After this, he completed a full mandate as president of the International Astronomical Union. For his contributions to Dutch astronomy and to society, Adrian Blaauw was made Knight in the Order of the Netherlands Lion and a member of the Royal Dutch Academy of Sciences. He received many other honorary awards. He returned to the Kaptein Institute after his retirement in 1981 and passed away in 2010 at the age of 96. The Blaauw Chair and Blaauw Lecture were initiated in 1997 as one of 6 visiting professorships in the Faculty of Science and Engineering, and is selected by the scientific staff of the Kaptein Institute through advice to the board of the faculty. Thus far, we've had the pleasure of welcoming 18 Blaauw professors at the University of Groningen, and it is my honor to introduce today Professor Tim de Zeeuw. But before I proceed with my laudatio, I would like to mention that Professor de Zeeuw knew Professor Blaauw himself very well, and that makes this lecture and occasion all the more special. Tim de Zeeuw is full of wonderful anecdotes about Adrian Blaauw. Some of these anecdotes he has shared with us during the time he has already spent at our institute, and some other anecdotes we will probably also hear about this evening. This admiration has allowed us to learn, as Tim de Zeeuw himself once stated, that Adrian Blaauw was a very special person who exerted a very positive influence on the world around him. As former graduate student of Tim de Zeeuw, I was lucky not only to come to know Adrian Blaauw through Tim's anecdotes and admiration, but I also had the opportunity to witness myself what a great source of inspiration Professor Blaauw was. On many occasions, I saw him seeking the younger generations to enthusiastically discuss science, even when he was well past his 80th birthday. But let me now proceed to introduce Professor de Zeeuw to you. He's a world-renowned scientist and a very influential figure in the astronomical world. Tim de Zeeuw received his cum laude PhD degree in astronomy from Leiden University in 1984. He worked at the Institute for Advanced Study in Princeton and at Caltech before returning to Leiden in 1990 as professor of astronomy. He was the founding director of NOVA, the Netherlands Research School for Astronomy, which coordinates different aspects of astronomy across the Netherlands. He directed Leiden Observatory and was Director General of the European Southern Observatory for a decade, just like Adrian Blaauw had been in the past. Professor de Zeeuw returned to Leiden University last year and holds a visiting professorship at the Max Planck Institute for Extraterrestrial Physics. Professor de Zeeuw's research interests concentrate on the structure and dynamics of galaxies, including around the Milky Way. His aim is to establish the properties of dark matter halos around galaxies, to probe the supermassive black holes, and ultimately to understand how galaxies have formed and evolved. A significant second line of research is the study of groups of young stars in the vicinity of our Sun, which got started thanks to Professor Adrian's Blaauw influence. Although trained as a theorist, Professor de Zeeuw gradually became involved in the development of new instrumentation, as we will hear later tonight. Tim de Zeeuw's track record is absolutely impressive. He has co-authored 235 refereed papers, and these have garnered over 24,300 citations with an H index of 83. He has guided the research projects of more than 90 master students, graduate students, and postdocs, many of whom have tenured positions in astronomy. Professor de Zeeuw has received many prizes and holds also 3 honorary doctorates. Tim de Zeeuw has chaired many prestigious boards and has played a crucial role in the European vision for astronomy over the past decade, including, of course, during his directorship of the European Southern Observatory. During his mandate, the Very Large Telescope on Paranal in Chile was equipped with new powerful instruments, new wide-field telescopes saw first light, and the construction of the Extremely Large Telescope, the largest telescope in the whole world, with a 39-meter diameter main mirror, was started, with first light expected for 2025. All of these aspects will undoubtedly be discussed in tonight's lecture, The World's Most Advanced Eyes on the Sky. Please join me in giving a very warm applause to this year's Blaauw Chair, Professor Tim de Zeeuw.
Ladies and gentlemen, thank you very much. Amina, thank you for the kind words. I'm particularly very grateful that the Kaptein Institute and the Groningen University have appointed me to this position, the Blaauw Professorship. And as you have already indicated, it is very special for me because he guided my initial steps in science, and we stayed in touch forever until he unfortunately passed away. So what I will do today is indeed tell you about what I call the world's most advanced eyes on the sky. You see some of them in this picture, which is a picture of the Paranal Observatory. You see the Milky Way. But before getting into this, I want to say still a few words about Blaauw, and there will be a few others that will come through the talk. Very gifted scientist, major leadership role in both national and international astronomy. And you have already indicated some, but that included, but was by no means limited to leading ESO for 5 years. And since I'm your advisor, I mean, he was the second Director General, yes. But he had a key role in creating it. I'll come back to that. He was the president of the International Astronomical Union. And what not everyone knows, he held multiple appointments over the years in both Leiden and Groningen. I believe 3 times in Leiden, 2 times in Groningen, and then emeritus professor in both universities. And I doubt there are many who can say the same thing. He was also an excellent historian, especially after his retirement. He wrote the histories of ESO, the early history, the IAU, and he wrote histories about the village in which he lived, just outside Norge in Drenthe, and many other topics. And he was a great mentor, and you already indicated this. He's influenced quite a few people, many people in the field, and some of them are here in the audience, for which I'm extremely grateful. After his 5 years at ESO, he returned to Leiden for about 5 years as professor on the astronomy department, and he taught a lecture in galactic structure when I was a second-year student, and I was very excited about this because it was almost the first more detailed astronomy that we got to learn. And at the exam, I apparently wrote 18 pages in responding to all the questions, and it turned out a year or so later that Professor Blaauw had not forgotten this, because not every student did this, not be known to me, of course. He advised a small research project on the nearby stars, but he also made sure that as a theorist, I did get an opportunity to broaden my horizons, and he sent me to work with Martin Schwarzschild in Princeton, someone who is quite famous for understanding the internal structure of the stars, and that changed my life. We've had regular interactions ever since, and I think back very fondly to his trip to the Chilean observatories that he had helped create at the age of 95 in February 2010, and that was really impressive. You see 3 pictures here on the right in the prime of his life. The middle picture, he is awarding the doctoral exam, the master's degree, to an extremely young future Blaauw professor. And the bottom picture, we are looking at the sunset at the Paranal Observatory. Now, before we go to the meat of the talk, I want you to cast your mind back some centuries. I want to remind you of a scientific revolution that took place in the late, around 1600. Copernicus in 1543 published a book posthumously that explained that not everything in the universe, which at the time was considered only the planets basically and maybe the stars, were rotating around the Earth. The Earth was the center of the universe. That was not the case. The statement was the planets orbit the sun. This had been understood by some scientists in the centuries before, quite a few centuries before even, but it was not the official policy of, in particular, the Church. The Earth was the center of the universe. And the fact that he published a book, or it was published after he passed away, was on purpose. This way there could be no repercussions. And then around 1600, Italian priest Giordano Bruno had gotten wind of this, and he made a very bold statement that people have not always remembered. He said, look, if the sun is like a star, or if the stars, I should say, are like the sun, and they're only so dim, you can only see them at night because they are really very far away, well, if our own sun has planets, why shouldn't the other suns, the stars, have planets? And he even speculated that they might have life. It did not end well for Bruno. He had other ideas and he was burned at the stake. But this was right. And it then took Galileo, 10 years later. He used a Dutch invention, the telescope. I hope there are not too many Italians in the room. I see one, but okay. But he built his own telescope with a lens about this big and looked at the night sky. And then he discovered some really interesting things, and in particular, he confirmed that Copernicus' view was right. Now, how did he do this? If you look at it through today's eyes, he took advantage of a development in technology. And that's one of the threads in the talk. He was the first to use the telescope to study the heavens. He looked at the moon and discovered, hey, there are mountains on the moon. If you look at the rim, you can see it. He saw that the planet Venus has phases, just as the moon. And he saw that the planet Jupiter was accompanied by little pinpricks of light. Jupiter moves against the background of the stars from night to night, and he saw that these little pinpricks went with Jupiter and actually changed position. And he realized, hey, these 4, we now call them Galilean moons after him, they orbit Jupiter. So he was again something that was not going around the Earth. It proved essentially Copernicus' view. And he also looked with his telescope at the Milky Way, the hazy band of stars. We know it's stars, the hazy band in the sky. And he saw that with a little bit of magnification that he could do, that this was not hazy light, it was a whole bunch of stars. So, why could he do this? Because this little lens gave an advantage in two directions. It increased sensitivity. The lens is bigger than your eye, so it catches more light and it focuses it, so you can look a little to fainter objects. And it also magnifies the image, as we all know from using binoculars. So he increased the sharpness of what he was looking at, and that's why he could see mountains on the moon, which are harder to see with, at least with most people's eyes. And this step of taking a new development, this was a development we would now call in optics or engineering, and apply it to scientific questions, is what is been the thread that's been supporting astronomy ever since. And I want to just very quickly mention 4 giant steps. There are many in between, but 4 are quite important, I think. So his telescope used lenses. We call that sometimes a refractor. It bends the light. So to get more sensitivity and more sharpness, you build a bigger lens. You polish the glass and you get a bigger lens. But you have to follow the stars as they go slowly across the sky, because we rotate under the sky, so to speak. And that means your telescope changes its position. And if the lens is very big, it bends. The glass is too heavy, and it blurs the image. And the practical limit was reached with the venerable Yerkes telescope, an observatory near Chicago, where Blaauw also worked in the 50s. With a lens of about 1 meter diameter. It's a giant Galilean telescope. But the opticians realized you can also magnify and focus if you use mirrors. More than one mirror, you focus it at another point and then you can look at it. And mirrors are only reflecting on one side, and on the other side you can support it. So you can build a much bigger and therefore more sensitive telescope. And indeed, the practical limit for single pieces of glass that can be polished to a really good shape is about 8.5 meters or 8.4 meters. The Very Large Telescope in Paranal has 4 8.2 meter mirrors, and you can see a picture roughly to the scale of the picture that shows the Yerkes telescope on the top left. There is a very famous physicist standing under the telescope, who some of you will no doubt recognize. The hairdo in 1921 was unusual, Professor Einstein. It's to the same scale as the mirrors that now go in the VLT. And they're actively supported from the back, so that whenever the telescope changes its position, the glass stays in perfect shape, the aluminum on it focuses all the light, and you get a beautiful picture. So, better telescopes, reflectors. There's also better detectors. In the old days, so to speak, you looked through a telescopes with your eye. Great, you can see beautiful things, you can draw them, but you cannot integrate. The longer you look, after your pupils have dilated a little, you don't see fainter and fainter objects. It's just instantaneous. Then the photographic plate was discovered, photography was discovered, and you put an emulsion on a glass plate and you can expose for an hour and go, therefore, deeper, more sensitive. Photographic plates are not particularly sensitive. It was a huge step forward because you could integrate. The electronic detectors that came in about 40 years ago, in which I bet nearly all of you have in your iPhones, they are 50 times more sensitive. And therefore, with the same telescope, but with this new detector, you could suddenly not increase the sharpness, but you could look at much fainter objects because the detector catches more light. Third step, spectroscopy. Difficult word perhaps, but if you let the light that you collect fall through a prism, it splits up in different colors, the colors of the rainbow. That we call that the spectrum. And if it's a hot object, it will give you colors from the ultraviolet to the red. If there is a colder object, a cloud of material in between, then that will absorb some of the light, and you get dark lines in the spectrum, as you see on the top right. And the solar atmosphere is cooler than the center, still hot, but it's cooler. And therefore, if you look at the sun with a prism, you see lines in the colors of the rainbow. And those lines are the fingerprints of atoms and sometimes molecules. So by doing this, you could suddenly learn about the chemical composition, the composition of the material. You can learn something more than simply make a picture. And the fourth step that I want to remind you of is that there is not only what we call visible radiation coming from the universe. Our eyes are most sensitive to yellow light. Why do you think that is? The sun sends out most of its energy at yellow wavelengths. And we have evolved biologically to take advantage of this. But there are X-rays, there is infrared radiation. If you look at the coals in a fireplace and the fire dies down, it gets redder and redder. And when you don't see a color anymore, but you put your finger on the coal, it's still hot. But the radiation is so red that the eye doesn't detect it anymore. We call that the infrared. And similarly, it's possible, there's even radio waves that you can listen to. So traditionally, the telescopes, and I will restrict myself mostly to those, look in the visual wavelength range. About 80 years ago, radio waves from outside Earth were discovered, but nothing else, because our atmosphere protects us from X-rays and all kinds of other radiation that would be quite unhealthy for us. But 60 years ago, our society got the capability to launch machines into space. So you can go above the atmosphere and detect X-rays or gamma rays, whatever, and study the universe in that way. So you have suddenly many more tools to try to learn what's out there in the universe. And what these telescopes on the ground and in space and at these different wavelengths have told us is that we live in a very strange and wondrous universe. There are planets, there are comets, there are many, many, many stars, but also many fuzzy nebulae. And some of these turned out to be hot gas in our own Milky Way, still at substantial distances, but others turned out to be whole individual galaxies. The Andromeda Nebula, those of you with very sharp eyes and on a really clear night here in the north might be able to see it. Some of these others are entire Milky Ways, but at giant distances, which is why they appear so small and faint. And the result is that Copernicus was certainly right, but it was certainly not the Earth the center of the universe. It was also not the Sun the center of the universe, or even our own Milky Way. It's an incredibly large universe. And our Milky Way is only one of these, what we call galaxies, these large collections of stars, where the Sun orbits the center in 250 million years. There's 100 billion stars in our galaxy, and there are at least 100 billion galaxies visible to us in principle. So that's why I wrote, but then the space ran out on the slide, that the universe is very, very, very large. I could have added a few more varies, and it's full of galaxies. And we live in a very interesting time that the telescopes of today allow us to see all the way back in time. And I have only one equation in this talk, and it's this one. I've written it in words. All you need to remember is far away is long ago. It takes light time to get somewhere. It moves very fast, but not infinitely fast. And if you have really far away objects, they will be quite faint. But the telescopes are now powerful enough to see them, all the way back to the beginning of the universe, about 13 billion years ago. And that means that on a clear night, when you're out in the fields near Baden or somewhere else here in the north, and you look at the night sky, you should realize you're looking at a history book. Astronomy is not only a hard science, it's also history. And the telescopes have shown that the universe has a large number of amazing things in them. I'll come back to we can measure the motions of stars in other galaxies. We can learn things, and I'll come back to that, about the black hole in the center of the galaxy, etc. And what has also happened is that these same telescopes of today allow us to finally confirm that what Giordano Bruno postulated, that boy, if the stars are suns, they could well have planets, that was the subject of science fiction and philosophy and multiple movies and books until about 20 years ago, when the technology was good enough that you could actually prove, hey, this star has a planet, and in some cases you can take a picture. And that changes our worldview too. If there are 100 billion stars in our galaxy and nearly all of them have planets, makes you feel pretty insignificant. At least it works for me, but I'm from light also. Now, before going to the best ground-based telescopes, I want to say a little bit about space telescopes and pay homage here also to another giant of our field, Professor Lyman Spitzer, who in 1946, think about it, this was 11 years before Sputnik, in 1946 wrote a detailed study for the Rand Corporation where he proposed that our society should start launching telescopes above the atmosphere. It was quite visionary, and it led to a whole series of space missions, not only in the optical but also in X-rays, and it culminated in, that was really his vision, the Hubble Space Telescope, which was launched in 1990 and is still going strong and has become an icon for science. It has, by today's standards, a fairly modest mirror, 2.4 meter diameter, but it's in a really good location, 600 kilometers above the atmosphere, I mean above us. And it had the advantage that the astronauts could go there with the space shuttle and upgrade it and fix it in a number of cases. And that was and continues to be quite remarkable, and it's one of the advanced eyes that the talk is about. And everyone hopes that in a few more years it will be succeeded by a 6.5 meter telescope named after James Webb, a former NASA administrator. And it has changed our field. Beautiful images of star-forming regions, images of the deepest images of the high redshift universe, etc. What happened, much less visible to the media and the public perhaps, was that in parallel there was another revolution happening. And this actually connects with Adrian Blaauw. The field of astrometry, which was quite venerable, which is the field of determining where everything is in the universe, or at least in the sky. What are the precise positions of the stars and how fast do they move? Everything moves, but they're so far away that it really takes high precision to see that. And doing that from the ground was really very difficult. The atmosphere makes things problematic. You can't see the whole sky from any particular point. You have to connect data or observations from different locations. And the breakthrough came in 1989 when ESA, the European Space Agency, launched the Hipparcos satellite. That had a technique in space of continuously scanning the sky, very clever, which then allowed to work out the exact, the much more precise positions and motions of the stars. It was a fairly small mirror. There is a very small icon, an image of it on the top left. It could observe about 100,000 stars in the sky with precision in distance, or 1 over the distance. The astronomers call that parallax, of a milli-arcsecond. Now, if you go once around, it's 360 degrees. So when you take 1 degree, you divide it by 60, you get an arc minute. You divide it again by 60, you get an arc second. And our eyes are, if you look at something in a distance, you can, with the naked eye, maybe separate 10 or 15 arc seconds. And Hipparcos could determine, telescopes do a little better, Hipparcos could do 1 milliarc second, so really very accurate, and it could measure the motions of the stars. And these 100,000 stars had to be, at that time, selected in advance, and that was done by a team in Europe under the leadership of Adrian, because he was clearly the expert in this whole area. He was very committed to this, and he basically organized that field. And what is quite interesting is that Hipparcos was such a success that ESA followed this up with a mission called Gaia, which was launched in 2013 and is still doing this. 100 times more accurate, 10 micro-arcseconds, and not for 100,000 stars, but for 1.7 billion. That shows you what technology does in 25 years' time. Couldn't be conceived even almost in 1989. And I have one result in honor of the introduction, of course. As far as I know, there was a press release at 7 o'clock this evening, or at least today. Professor Helmy has done much work with the Gaia data, with her team here in Kaptein, and has discovered in the motions of all these stars that can now be measured that about 10 billion years ago, a long time ago, but not in a galaxy very far away, it's in our own galaxy, a smaller object, like the Magellanic Cloud, fell in and was engulfed by our own galaxy and created much of what we now call the stellar halo. And she has very aptly named the object Enceladus, because Enceladus in Greek mythology was one of the sons of Gaia and the sky, Uranus, and in a big fight was buried under Mount Etna and still is the cause for seismic activity. So even today we can sense that Enceladus is there because Etna still now and then is active. And similarly, with observations taken today of the Milky Way, you can learn about what has happened in the Milky Way 10 billion years ago and ever since. Let me now turn to ground-based observatories, and indeed the European Southern Observatory, which I am extremely fond of and obviously also had a major connection with Blaauw. It is an intergovernmental organization for astronomy, which means it's based on a treaty between governments. Not a few institutes, not even funding agencies, but governments. And the initiative came from Professor Jan-Hendrik Oort and a German visitor, Walter Bade, who had emigrated to the United States in the 30s and was an expert, or maybe even a little earlier, but was visiting Leiden a few years after the Second War. And they discussed the state of astronomy in Europe. And at the time, one should think back, the largest telescope that astronomers in Europe had access to was about 1 meter size diameter, the mirror. And there were no no good detection techniques. The Californians used private funds from very wealthy individuals to build a 3 meter and even the venerable 5 meter, 200-inch telescope on Palomar that was ongoing. And Oort and Bade realized, if astronomy in Europe wants to rebuild itself, we need to do something. It's good to have friendly scientific competition, but we also need to do something. And the result was that they realized that the countries couldn't do it alone. But if they worked together, they could probably do it and build a serious telescope. And that led to Oort then went to work with some others to convince colleagues in a number of countries, led to a formal declaration in 1954. And 8 years later, ESO was officially founded by the 5 countries indicated here: Belgium, Germany, France, the Netherlands, and Sweden. And the goal, which to many of the younger people in the audience may look slightly modest, was to build a giant telescope in the southern hemisphere. And giant meant about 3 meter size, main mirror. And in the south there was a lot to discover. There were relatively few telescopes, and what was not spoken was that, well, if you want to compete with somebody who's building a 5 meter, maybe you go to the other half of the sky and do your observations there, but that wasn't spoken. If you look today, ESO has 16 member states, Australia is since a year a strategic partner, and it has observatories on La Silla, which I come back to in a moment, the original one, and on Paranal, and also on Chasnantur in Chile. And I'll show you a little bit about this. But you might ask, or I will ask, why Chile? Because at the time of the creation of ESO, the thinking was we will go to Namibia. And I'll come back to that as well. Now, why is ESO and other observatories in Chile? It's pretty clear from this picture, I hope. If you look at the left, you see in the left top corner the Hubble Space Telescope. This picture is taken from 600 kilometers up by Claude Nicollier, a Swiss astronaut, who was with the other colleagues going to Hubble in the mid-90s to go and fix it. And you look up towards the right of the picture, you see most of South America, towards the tip of the picture, which is the Strait of Magellan. And if you look a little closer, what you see is essentially all of Chile. The clouds remain on one side, on the top, they remain behind the Andes over the Amazon region. There's a lot of moisture there, but it stays on that side. And on the side towards the right bottom corner, it is over the ocean. And that is because the Humboldt stream keeps the Pacific extremely cold. It's not nice to go swimming there, but it's great for astronomy because the clouds are either over the ocean or on the other side of the mountains. And the result is one of the driest deserts in the world, the Atacama Desert. And it's there that the telescopes are, because if it's clear every day, maybe it's clear every night, and you can observe every night. And the first observatory, I should show you one more thing here. On the right, you see a picture taken with a satellite of the transparency of the air, and darker means more transparent. And the area, you can maybe read, the capital of Chile is just below the slide, and then you see La Silla, and then Paranal and Chasnantur. That's where the telescopes are, so good location. The first observatory was at the southern edge of the Atacama Desert on a mountain called La Silla, the seat. And this is a picture of it in its heyday. Lots of little domes, 60 centimeter, 1 meter telescopes. And then the scene is dominated by the giant dome in the back, which holds the mighty 3.6 meter telescope, which was the goal of ESO. And it is fair to say that much of the achievement of the countries to build this very respectable observatory has the hand of Adriaan Blaauw in it. I mean, that's on the next slide actually. He had a key role in creating ESO. He stayed in the United States between 1953 and 1957, and I have the feeling that some of the daughters were on that trip. At least I've seen some pictures. And then came back to Kaptein, as already mentioned, Kaptein Institute, and in 1957, and Jan Oort instantly, of course, pulled him in, or he probably volunteered for it. He initiated site testing in Namibia with André Muller and Bert Bosker, who were young men here in Groningen, and he said, look, you guys, why don't you go to Namibia for a few months and try to work out what the conditions are? But he was also secretary of the ESO committee, which was the council of ESO before it was created, until the creation. And with Jan Oort pushing and Adriaan making sure that everything was okay, was an extremely powerful combination. And he became Director General in the period indicated on the slide, and was influential in bringing the headquarters from Hamburg, where the first EG worked, Otto Heckmann, to Geneva on the campus of the CERN laboratory, so that the ESO staff could learn from the engineers how to build a big telescope. That's not something you do with a few students, but you have to really have big firms involved. And he managed to do that. And his big achievement, I think, is to make La Silla a big success and to have the 3.6 finished. And in those 5 years, he also had to deal with the well-known coup d'etat in Chile when Allende was killed and the junta came. And that requires significant diplomacy if you're a guest in a country and all of this is happening. He wrote a history of ESO, and I already mentioned the visit in February 2010. Here he's looking out from the catwalk on the 3.6, look out over his observatory. It must have been really special after so many years to see again what you had a hand in. And it was. Now, after the creation of La Silla, the countries realized, this is actually working, this partnership. Why don't we do something else? Why don't we take the next step and again take advantage of technology? And that led to the creation of the Paranal Observatory. Here's a picture taken in 1987 of the mountain in the north, close to the ocean. And the bump in the back is Amazonas, to which I will come back. And it took still a few years, and it took the next DG. After Blaauw, there was another Dutch DG, Lodewijk Woltjer, and then Harry van der Laan was appointed Director General, and I'm extremely pleased and honored that Harry is here this evening. And if I remember correctly, Harry, you actually made the decision where to put the VLT, Paranal. This is what it looks like today. You look west, you see it's a very dry desert. You see the clouds over the ocean. If you look very closely, you can see the ocean just under the clouds, 12 kilometers away, and one of the driest spots on the planet. The humidity is sometimes less than 1%. That's not really healthy. Here's a picture from the other side. There are 4 unit telescopes, very boring name, with the 8.2 meter mirrors. There are 2 survey telescopes, the VST and Vista, smaller, 2.5 and 4 meters. And there are 4 little auxiliary telescopes, each with 1.8 meter diameter mirror. And all of it is run from the structure that is labeled control building. Here's a picture of one of the 4 8 meters. At sunset, the dome is open. And if you look closely, you can probably see, I don't have a pointer, and it's very difficult to point at 2 screens at the same time with accuracy. You can probably see the mirror lying in its cage under there. And you all know how it works. The light comes in from the universe, bounces on the main mirror to the secondary, which you can see sticking out there on top. And it goes down and is sent in one of 3 directions, straight through or to the side where there are instruments. 4 telescopes, 3 positions each for an instrument. That's already 12 instruments, cameras and spectrographs. And then there are some more because the telescopes can even be used together. And that means there is a bit of technology on this very remote spot in the desert. And all of this machinery is a one-off. You don't buy it in a store, built in the member states of ESO. And it has to work when the sun goes down and it is clear, and that is essentially every night. And that's why there is quite a group of engineers on the mountain to make all of this happen. But it also shows you what an amazing amount of technology is being used to study the universe. Most of the instruments are built by consortia of institutes where ESO pays the hardware and buys it, and the institutes provide the person power. That's extra effort, and they get guaranteed time for it, which allows them not only to build the instrument because they're excited about the science you could do with it, but they can actually do it themselves. And I believe this is one of the key reasons, and I've written this down as well, for the success of ESO, because in this way you have an observatory that's not off by itself, but it is connected to a whole bunch of institutes, including Kaptein and Esron here as well, in the joint program. And I think here also Van der Laan needs the credit, has the credit for inventing this model, because this way there is a multiplication factor and you get a community working together. And again, Harry, that was brilliant. You see some of these instruments are not small. The one on the right bottom had to be constructed first in Lyon and then shipped. I mean, deconstructed, shipped in boxes, reconstructed at Paranal, and then moved onto the telescope, and it's a monster. It's called MUSE, Multi-Unit Spectroscopic Explorer, and it is, I want to show one or two results. It's called an integral field spectrograph, where you disperse the light in the colors of the rainbow, not in one little point, but over an entire field. And therefore you can study objects that have not much symmetry, and you can look at their chemical composition, you can look at the velocities, etc. And if you want to learn something about optics, the link here on the website is the website here on the slide shows you a movie of what happens to the light until it gets into the instrument. It's quite interesting. The instrument is aided by a technique called adaptive optics, where one uses artificial stars. You point some lasers at the sky, you know what the dots should look like. The atmosphere blurs them, you measure very quickly, you correct with movable mirrors the blurring and to get these laser dots sharp, and then they also correct the light of the object you really want to look at. And that way you can use, you can basically take out the effect of the atmosphere. And I have an example of this here. You can see on the left a globular cluster of a lot of stars, where in the normal mode you get a rather blurred picture, as you can see, especially if you blow it up in the middle, and then you turn on the adaptive optics, push the button, and it clicks into sharpness, the picture on the right. Another example is a picture of Neptune, planet actually observed by Galileo, but he didn't realize it. It's 4 arcseconds across. On the right, you see what happens if you look at it through the normal atmosphere. Not good. The middle is what Hubble sees, no atmosphere, very sharp. And on the left, not quite at the same time, you can see what the VLT now sees with adaptive optics. You see the clouds in the atmosphere of Neptune, and it's sharper than Hubble. And that's pretty exciting. Again, sharpness and sensitivity. The VLT has one other very unique aspect, and that is that you can use the telescopes together in a technique called interferometry, well known in the radio world. Westerbork is an interferometer, where you use the 4 big telescopes, for example, to mimic a telescope that is not a filled 130-meter dish, but at least it has the sharpness of the largest distance between the telescopes. So you get one of the two, not the sensitivity, but you get the image sharpness. And that can only be done if you build this whole machine from the start with this in mind, which is what ESO did in the 90s. And it cannot be done anywhere else in the world. And that gives you really stupendous resolution and still okay sensitivity, 2 milliarcseconds from the ground. It's not bad. And that is in particular very important for a study of the galactic center. And for that there was also a press announcement today. And I'm now going to try to play a video, which I hope will work, where we will travel to the galactic center. No? Yes. Some music comes out of my laptop, but let's ignore that. Keep watching at how many steps of magnification we're getting. Getting closer now. These are stars that are running on orbits in this very special spot in the galaxy. You see there is a spot in the middle that you now and then see, and then sometimes you don't. It flares. and the stars orbit this central point. It's like the planets going around the sun. And this I'll show you in a moment what this means. So at 25,000 light years, with the interferometer, we can actually, in fact even before that, we can actually see stars orbiting the central point in the galaxy. And if you measure the velocity in the line of sight, and if you then also measure the position of the stars on the sky, you can learn something about the size of the mass that they're orbiting. If the mass is big, the motions are higher. If the mass is small, the things move slower. So if you measure the properties of this star that's going around the galactic center, you can measure what that mass, the strength of the gravity is. It's 4 million solar masses, 4 million times the mass of our sun. And it's stuck in an area or volume, the size, it's a little bit larger than Groningen, but not much. We call it a black hole. Light cannot escape. The gravity is simply too strong. That means that you cannot describe this simply with what we call Newtonian physics. You have to use the general relativity that Einstein posited a century ago. And the team with the gravity instrument has shown this summer that indeed the orbit does exactly what general relativity predicts, that every time it passes very close to the black hole, the orbit precesses a little. And if you, I hope you can see this here on the right, the middle panel on the right shows little dots where this gravity instrument with the VLTI did a measurement almost every night. And every night you could see that the star had moved at 25,000 light years away. It was very close to the black hole. It happens every 16 years, and it was moving with 7,000 kilometers per second at the closest point. Must be quite a ride if you were on a planet orbiting that star, but it might also be a little risky for your health. And then today the announcement came that with these measurements they did, it is now possible to see that there's something happening very, very close to the center of that flaring object, where there's physics going on, magnetic reconnection it's called, really almost at the event horizon, as it's called, of the black hole. And that's never been seen before in any level of detail, and it's really quite an impressive technical feat. And for ESO to do that, and the Max Planck team led by Reinhard Genzel, Eisenhower and Oliver Pfull, to pull this off, the technology that's behind here is really amazing, and it's something 20 years ago we couldn't even have thought that you could do this. So pretty exciting telescopes. Now, let me say something very briefly about another project that ESO is doing. It's by some accounts you could say it's a radio telescope. It's called the Atacama Large Millimeter Array in northern Chile. It's many, many radio antennas, but they listen at very short wavelengths of between 7 and 0.3 millimeters. And it studies the properties of the cold universe, and it is a global partnership. It's important in astronomy. You cannot build this in your own country, certainly not in our country. You would only detect the water in the atmosphere, but it's simply beyond the capabilities of doing this. And ALMA is at a site in Chile. There is a base camp outside San Pedro de Atacama that's at 3,000 meters, the edge of the Salt Sea. And if you see the base camp here, and if you look up, the array is behind the mountains there in the middle at 5,000 meters. And here's a picture. 12-meter antennas, a whole bunch of them. They can be spread over the plane. They can be brought close in to change the resolution of the images you get and the data. You're at half the atmospheric pressure, which your brain is in denial about when you're there. You think you can think, but no, in some cases. But that's good, because then you've got already rid of half the atmosphere, and in a place that is as dry as this, there's almost no water vapor left. And in that way, there is no blockage from the atmosphere. If you put ALMA in the Netherlands, great for atmospheric science, not good for astronomy. But in this dry desert, it's really wonderful. It's like opening the curtains and suddenly being able to see another aspect of the universe. And what this has brought is that the jump over the existing facilities is so large, it was opened in 2013, is that it now is possible to study the formation of planetary systems. We know where the nearest star-forming regions are. They're at a certain distance. There's nothing we can change about it. So you have to build a facility that's good enough so you can actually take a picture and have the resolution. And that's what ALMA does. And it allows you to see structure in dust disks at the scale of the solar system. And in fact, the object on the right, you see there in the middle, there is a ring, and there is of dust, and then there is a gap. There's this black ring, and that's the size of the Earth orbit at that distance. And it may well contain a planet. So this facility is also studying exoplanets and star formation and asking the question, okay, if there are so many planets, how did all of this form? How does this happen? And that's what the facility can do. In the last few minutes, I have not many, don't worry, Amina, I'm finishing soon. I have one slide about the Netherlands and ESO, and then I will go briefly into the future. I already indicated that the Netherlands is the founding member, or one of the 5 founding member states of ESO. And it clearly has had a remarkable influence. It's not something I write on slides, but ESO is now 56 years old. And 60% of that period, the Director General was Dutch in an international partnership. It's quite odd. It's also quite nice. There's no pressure on the colleagues here to step up to the plate for the next one. But it's quite interesting, but I don't write this on slides because you never know, the colleagues see this. Strong involvement in many science programs, of course, but what is key is the instrumentation development. I showed you these pictures of this technology, and by having a telescope on the ground with so many possibilities to put instruments, you can build an instrument with today's technology, use it for 10 years, and in those 10 years, technology advances, and you do it again. And you make the telescope much more powerful again, without building a new telescope, that you can do too. And there is an important role also for the technical institutes and industry. And the Dutch home base for ESO is the organization NOVA, already mentioned in the introduction, collaboration of the 4 university astronomy institutes, Kaptein here, Leiden, Amsterdam, and Nijmegen now, that work together to make our use of ESO a success and make sure that the telescopes do what we would like them to do, and that we do that with them. And that's been supported by the ministry for at least 20 years already. And in the last 3 minutes, let me just say a few more things about what happens next. So it's quite clear, and even our American friends are now grudgingly admitting that the VLT in particular is the world-leading optical telescope. It's the most advanced telescope system in the world. And it is all created because of a vision of some of the geniuses of the past, including obviously Adriaan Blaauw. The next step is to take another jump in capabilities. In fact, the jump is larger than the jump that Galileo took when he replaced, so to speak, his eye with the small telescope. He looked with the eye through the telescope, but to make a lens of about 4 or 5 centimeters. This is a telescope, the extremely large telescope, which will have a 39-meter primary mirror. That's larger than this room. It's not a single piece of glass. If you could make it and polish it, you could never move it anywhere, because how do you do that? So it's a whole bunch of hexagonal segments that all sense each other and that have to at any moment form a perfect mirror. It will be a stupendous machine to study exoplanets, the deep universe, many other problems. And it's going to be built on a mountain actually very close to Paranal. There was a worldwide search and it became clear this was the best location. It's the bump I showed you early in the lecture, and I'll show it to you again in a second. Construction is on track for first light in late 2024, 2025. That's good, it's funded. All the contracts are running, the instruments are being built, and it's here also that one of the 3 first light instruments, METIS, is led by the Netherlands. And if you're in a partnership with 16 countries, and there are 3, including some quite big ones, and the first 3 instruments are being built, and you are the leader of one of the 3, you're doing something right. It's also a big responsibility, but hey, it's exciting. And the operations cost is secured. So here's a picture again of that region. We're now looking the other direction than the picture of Paranal before. You see Paranal in the foreground. It's rather small, but that's why there is the arrow and the little picture to guide your eye. And then you look east in the direction of the Andes that you see on the horizon, 200 kilometers away. And about 25 kilometers across the valley, there is this bump Amazonas, 3,000 meters high, which is where the ELT will go. It was possible to convince the Chilean government to expand the area they donated for the VLT in 1995, to expand it east. All that land is ESO's, belongs to the member states, and it's larger than the Flevopolder and half the Noordoostpolder. However, there is no water. It's certainly not below sea level. There are no people, there's no life, there's nothing except telescopes. And this is an artist's impression of the mirrors. And I don't want to go to the details, but the big cup at the bottom, the main mirror, is 39 meters across, and the secondary, all the way up there, will be 60 meters up in altitude. And all of this will be built inside a dome, which will therefore be nearly 100 meters across, 80 meters high, and has a door that opens, 40 meters wide, obviously, because the mirror is big. That sounds like the arena in Amsterdam or in Munich or wherever, except it also has to rotate. Those are not so frequent in soccer stadiums in Europe. So it's really a big technological challenge, but that's ongoing. And I show you here again what it will look like from the inside, looking down on the mirror. When we got the territory from Chile, we then of course took the top of the mountain, because you have to make space for the telescope. We built a road around it. You're an astronomy organization, but you get into aspects like taking tops of mountains, building roads, getting power cords, all of this stuff. But it's needed because that's how you get progress in astronomy. And this picture appeared, I think, yesterday or the day before on the ESO website. It's an aerial picture taken with a drone of the top of that same mountain. The big trench is there for the foundation of the dome, and in fact the concrete, the first layers of concrete had been poured, so work is really going on. And this is what it will look like in about 6 years' time. And it will be, we all believe it will be the world's most advanced telescope for quite some time to come on the ground. So this brings me to the end of the lecture. I hope I have shown you how important technology is for the science of astronomy, but I hope I've also shown you that the kind of questions that astronomy is trying to answer are pretty broad questions, including, are we alone in the universe? There are other planets, is there life? I'm not saying there has to be a second set of humans who also spend most of their time, unfortunately, on social media, but it could be dinosaurs, it could be grass, it could be frogs, who knows? And that shows how very insignificant potentially our society may be in the big universe, or maybe not. We don't know, but we will find out with machines of the kind that I've shown you. And I thought it was particularly fitting to take this topic because it shows also how Blaauw in particular, after whom this lecture is named, had a key role in making ESO work and making it, basically building its first observatory in Zeeuw. Thank you very much.
Thank you very much for this very interesting lecture showing how astronomy and technology go hand in hand. We now have time for questions. If you'd like to ask a question, please raise your hand and we'll get there with a microphone so everybody can hear your question. So the floor is open now.
Wow. Well, I mean, what I would do in a lecture course is I would volunteer one of the persons in the audience to ask a question.
I don't do these kind of things.
One volunteer.
Tim, could you estimate for how long the ELT will be the largest and when it will be surpassed by a bigger telescope?
Thank you, Huug. It's quite an interesting question. There are two competing projects which are 30 meters and 24 meters. They don't have all their money. They don't have, in one case, they don't have a site. So if all continues to go well, ESO will have the ELT not only the biggest and therefore the most powerful for the science, but also will even have it first, which was certainly what was driving me to push the project. If you think about what could happen next, it is actually possible to build even larger telescopes, according to all our computer models, but it becomes really very expensive, and it's not obvious that that will work very quickly. So I don't think that the next step will be an even bigger one, but it might be more interferometry or some other technique. So it could be quite some time. I mean, it took, 40 years before the 200-inch was really surpassed. The Russian telescope first didn't work, then it did. And this one could certainly be there for 40 plus years, I think, despite the fact that technology advances very quickly. So let's see. There's certainly enough to do with a machine like this.
So, were there any plans to build auxiliary telescopes together with the ELT to create an interferometer? Or if not, why not?
It's, again, a good question. I wanted 2 of these, but it doesn't quite work on that mountain, and it's getting really expensive. I can show you, it was written. But the key part of the decision to go to Amazonas is that it is only 25 kilometers from Paranal. It will be run from the Paranal Observatory, from the same control room, and it is part of a whole system of 4-8 meters and the interferometer, which will still have a higher resolution, but not the sensitivity. And therefore, what happens next may well be interferometry, but maybe not directly on this mountain. But the fact that it is a system is going to be extremely powerful because there are so many things to do with this machine, but also still so many things to do with the existing machines. So it's quite exciting. 6 years.
Hello. Have you already decided on the first picture you're going to take with the ELT?
I stepped down. My second term came to an end 16 or 14 months ago. I don't make that decision. I think what will happen...
I mean you in the sense of ESO in general.
Okay. I think it may well be a very boring picture, and it may even be one that we can guess, because what is often done in ESO history at least, is that one takes a picture of what is called a globular cluster, one of these very dense star fields. And for the VLT, it was Omega Sun, a very big globular cluster in the southern hemisphere. Who knows? That might be the one. Yeah. But if you have an ID, let me know.
There's a question here in the front.
Yeah, and here too. But,
Yes. Yes? No? Okay, over there. There's two questions.
Do you think it will be possible in the future to let the ELT and the VLT work together to get even better resolution?
Maybe. But it has to, it requires still some technology to make that work without connecting the telescopes optically as it's done under the platform on parallel. I'm sure there is some enterprising young woman somewhere with a great brain that will tell us how to do that. Could even be a man.
There's a question there.
What is the field of view of this big telescope in seconds or minutes?
I believe this is about 5 by 5 arc minutes. It may be interesting for you to also realize that the field of view of the gravity instrument that looks at the galactic center black hole is 0.6 by 0.6 arc seconds, where on a night of good seeing, good observing conditions, that's about as sharp as the normal telescope can see because of the atmosphere, but because of the interferometer and some tricks, you can do that. So by that scale, 5 by 5 arc minutes is quite a substantial field.
Other questions? There's one over there.
Yes, I have two questions, if that's okay. First of all, could you elaborate maybe on the telescope that's being built in China, the radio telescope in the crater, if I'm not mistaken? And second of all, you touched briefly on the fact that it's, by the scientists in the field, conceived as a friendly collaboration between continents. Is that actually true, or would you say there's still kind of like a space race going on, or like a competition in that sense?
The first one, this is a telescope called FAST, which is a larger version than the famous Arecibo radio telescope, which was blown up in the GoldenEye James Bond movie some years ago. It's not a crater, it's a rather circular valley which happened to have a village in it, but the authorities decided everyone had to move and the village was destroyed, and now the whole thing is a radio telescope. As to competition, I think it is generally friendly, and the example that I usually give is quite apt at this moment. There is a competing team at the 10-meter Keck telescope that has also been studying the galactic center. And the race was quite equal, the competition on this was quite equal until a year and a half ago. And that was quite good. And it then became unequal because ESO has the interferometer and the gravity instrument, and they can't do that. But in those years, since the beginning of the VLT, this is one of those examples where without that competition, we would know less about the galactic center, but also both observatories would not have had as powerful instrumentation that they now have, because it was driven by a good, it's not so much the Cold War, it is more a sports competition. You train, you practice, you try to get to some of the results first, and I think that's good.
So I would like to close here. I have one question, last one. So it's along similar lines of what was asked before, but what do you think will be the first big discovery made with the ELT? Do you dare to make a prediction as a theorist?
This lecture is recorded. No, I don't have any prediction. We can discuss it afterwards.
Okay, let's
usually, sorry to interrupt you, but usually the reasons to build a telescope are at the time extremely good. And indeed, sometimes what it was built for actually works out, as we've seen with Gaia as well, for example. And in some cases, time passes and the field changes, and there is a new opportunity, and that is what you use it for. And that may happen again, which is actually exciting because it means we don't know the answers.
Okay. So on that note, let's thank our Blaauw hoogleraar for the Blaauw lecture today. I have a couple of presents from you from Studium Generale, who organized the lecture this evening.
Come down.
You want to step down? This is from Studium Generale.
What's this?
For drinking. For water.
Sustainable water
For your
supply.
next trip to Alma. And this is a book actually from the Kaptein Institute about the history of the University of Groningen, the University of the North. And this particular volume goes about the beginning of the 20th century when Kaptein played a crucial role.
Yes.
And so we hope you like it.
Thank you very much.
And let's thank Team de Zeeuw again. Final announcement, if you're interested in astronomy, on November 13th, there will be another special lecture by, this time by Professor Evine van Dishoek, who was recent recipient of the Kavli Prize at the DOT, also organized by Studium Generale. Have a good night.